Welcome to our lecture on probability theory. My name is Konyurkuljayeva Maral, and I'll be guiding you through this fascinating branch of mathematics today. Probability theory is everywhere around us, from weather forecasts to financial markets, from medical diagnoses to sports analytics. It helps us make sense of uncertainty and randomness in a systematic and logical way. Throughout this lecture, we'll explore the fundamental concepts that form the foundation of probability theory, and by the end, you'll have a solid understanding of how to quantify uncertainty and make predictions based on probabilistic models. Whether you're a student of mathematics, engineering, economics, or any field that involves data and decision-making under uncertainty, this knowledge will prove invaluable. So let's begin our journey into the world of probability, starting with the basic question: what exactly is probability theory, and why is it so important in both science and everyday life? So what is probability theory? At its core, probability theory is a branch of mathematics concerned with the analysis of random phenomena. But what do we mean by random phenomena? These are events or processes where the outcome is uncertain and cannot be predicted with complete certainty before they occur. Think about tossing a coin, rolling a die, or predicting tomorrow's weather. In all these cases, there's an element of randomness involved. Probability theory gives us the mathematical tools to model and analyze such situations. It allows us to quantify how likely or unlikely different outcomes are, and it provides a framework for making rational decisions in the face of uncertainty. The applications are truly vast, ranging from physics and biology to finance and artificial intelligence. When you understand probability theory, you understand how to think about chance and randomness in a rigorous mathematical way, which is why it's considered one of the most important branches of modern mathematics. Let's take a moment to understand the goals and learning outcomes of this course. The primary goal is to study the fundamental concepts and methods of probability theory, random variables, and probability distributions. We want to develop your skills in solving probabilistic problems and analyzing random phenomena. By the end of this course, you should be able to understand probability concepts and methods thoroughly. You'll learn to analyze probability distributions and expectations, which are essential for understanding how random variables behave in different situations. You'll also be able to apply probabilistic methods to real-world problems, bridging the gap between theory and practice. In terms of competencies, we'll focus on developing your analytical thinking, problem-solving abilities, data analysis skills, and information and communication technology skills. These are all highly valuable in today's data-driven world, where the ability to work with uncertainty and make informed decisions based on probabilistic reasoning is increasingly important in virtually every professional field. Let's begin with some fundamental concepts. In probability theory, an event is simply a set of outcomes of an experiment, but events can be classified into different types based on how they behave under a fixed set of conditions. The first type is a reliable or certain event which always happens. For example, under normal conditions at 20 degrees Celsius and standard atmospheric pressure, water is liquid. This is certain and predictable. The second type is an impossible or null event, which never happens. Under the same conditions, water being solid is simply impossible, as it would require temperatures below freezing. The third and most interesting type is a random event, which may or may not happen. For example, when we toss a coin, it might land on heads or it might land on tails. We cannot predict with certainty which outcome will occur, which makes this a random event. Understanding these three categories is essential because probability theory is primarily concerned with random events, where we need mathematical tools to quantify the likelihood of different outcomes. Now we move to some important distinctions when working with events. First, events are classified as incompatible if the appearance of one of them excludes the appearance of other events in the same trial. In other words, incompatible events cannot occur simultaneously. For example, when tossing a coin, getting heads and getting tails are incompatible because both cannot happen on the same toss. On the other hand, if events can occur simultaneously, they are called compatible events. For instance, drawing a card that is both red and a king is possible, so these events are compatible. Another crucial concept is that some events form a complete group if, as a result of a trial, at least one of them will certainly appear. In other words, the occurrence of at least one event from the group is guaranteed. For example, when rolling a die, the events of getting 1, 2, 3, 4, 5, or 6 form a complete group because one of these outcomes must occur. Understanding these classifications is vital for correctly applying probability formulas and solving problems effectively. This brings us to the classical definition of probability, which is one of the most fundamental concepts in this field. The probability of an event A is defined as the ratio of the number of favorable elementary events for this event to the total number of all equally possible incompatible elementary events that form a complete group. In simpler terms, probability equals the number of ways the event can happen divided by the total number of possible outcomes, assuming all outcomes are equally likely. This is expressed by the formula P of A equals M divided by N, where M is the number of elementary events favorable to A, and N is the number of all possible elementary events in the trial. For example, when rolling a fair 6-sided die, the probability of rolling a 3 is 1 divided by 6 because there's one favorable outcome and 6 possible outcomes in total. This classical definition works beautifully for situations where all outcomes are equally likely, such as games of chance, but it's important to remember that in real-world situations, outcomes may not always be equally likely, which is where other definitions of probability come into play. Let's examine the key properties of probability that follow from this classical definition. These properties are essential for understanding how probability behaves in different situations. First, a reliable event, which always happens, has a probability equal to 1. This makes intuitive sense. If something is certain to occur, its likelihood is 100%. Second, an impossible event, which never happens, has a probability equal to 0. If something cannot possibly occur, its likelihood is 0%. Third, and most importantly, a random event, which may or may not happen, has a probability strictly between 0 and 1. The probability could be very close to 0, like the chance of winning the lottery, or very close to 1, like the chance that the sun will rise tomorrow, but it will never be exactly 0 or 1 for a genuinely random event. This leads us to the general rule that for any event A, the probability must satisfy the inequality that 0 is less than or equal to P of A, which is less than or equal to 1. This range defines the entire spectrum of probabilistic possibilities and provides a consistent framework for all probability calculations. Now we need to distinguish between probability and another important concept, relative frequency. Relative frequency, often denoted as W of A, is defined as the ratio of the number of times an event occurred to the total number of trials. The formula is W of A equals M divided by N, where M is the number of times the event occurred and N is the total number of trials. For example, if you take 24 shots and make 19 hits, the relative frequency of hitting the target is 19 divided by 24. But here's the crucial difference. Probability is calculated before the experiment based on theoretical considerations, while relative frequency is calculated after the experiment based on observed results. Probability represents the theoretical likelihood, while relative frequency represents the empirical observation. This distinction is fundamental in statistics. As we conduct more and more trials, the relative frequency tends to approach the theoretical probability, which is known as the law of large numbers. Understanding this relationship between theoretical probability and empirical frequency is essential for bridging the gap between mathematical models and real-world observations. Probability can also be applied to geometric situations, not just discrete outcomes. This brings us to geometric probability, where we consider lengths and areas instead of just counting outcomes. In the diagram shown, we have a segment AB that contains a smaller segment CD. If a point K on AB is chosen at random, what's the probability that it falls on CD? The answer comes from a fundamental principle. The probability that a randomly chosen point falls within a smaller region equals the ratio of the measure of the smaller region to the measure of the larger region. In this case, the probability equals the length of CD divided by the length of AB. This makes intuitive sense, because the longer the segment CD is relative to AB, the more likely a randomly chosen point will land on it. If CD were half the length of AB, the probability would be 1/2. If CD were the entire length of AB, the probability would be 1. This geometric interpretation of probability extends our understanding beyond simple counting and allows us to handle situations where we have continuous ranges of possible outcomes. Similarly, we can extend the geometric probability concept to two-dimensional areas. In the diagram shown, we have a larger region J that contains a smaller region M. If a point K in J is chosen at random, what's the probability that it falls within region M? Following the same principle, the probability equals the area of M divided by the area of J. This is a powerful extension because many real-world problems involve two-dimensional spaces. For example, consider throwing a dart at a circular dartboard. If we want to know the probability of hitting the bullseye, it would be the area of the bullseye divided by the area of the entire dartboard. Or consider dropping a coin onto a floor covered with tiles, and we want to know the probability that the coin lands entirely within a single tile. These geometric probability problems are solved using the same ratio principle. The larger the area of interest relative to the total area, the higher the probability. This approach is incredibly versatile and applies to any situation where outcomes correspond to points in a continuous space with measurable area. Let's work through a complete example of geometric probability to see how these principles are applied in practice. Consider two concentric circles drawn on a plane with radii of 5 and 10 centimeters respectively. We throw a point at random into the large circle, and we want to find the probability that the point will land in the ring formed between the two circles. The key assumption here is that the probability of the point hitting any region is proportional to the area of that region and does not depend on its position relative to the large circle. First, we need to calculate the area of the ring, which is the figure we're interested in. The area of a circle is pi times the radius squared, so the area of the large circle is pi times 10 squared, which is 100 pi. The area of the small circle is pi times 5 squared, which is 25 pi. The area of the ring is the difference between these areas, 100 pi minus 25 pi, which equals 75 pi. The total area of the large circle is 100 pi. Therefore, the probability that a randomly thrown point lands in the ring is 75 pi divided by 100 pi, which simplifies to 0.75 or 75%. This means there's a 3 in 4 chance that a random point in the large circle will fall in the ring between the two circles. This example beautifully demonstrates how geometric probability W